Hello, you are welcome to this YouTube channel. In this video, we are going to be looking at the Lyapunov stability equation, and the theorem is here. It says let A be equal to, or let A be an element of a square matrix n by n matrix of a real number. Then the following statement are equivalent. They say all the eigenvalues of A have negative real parts, and the second condition states that for all matrices A equal to A transpose greater than 0, there exists a unique solution P equal to P transpose greater than 0 to the Lyapunov equation, and this is the Lyapunov equation. This is the Lyapunov equation. So we are going to be proving this theorem. So we are going to start with the Lyapunov equation, which is A transpose of P plus PA equal to Q. So we are to first of all ensure that all the eigenvalues of A has negative real parts. So we have this to be equal to this, right? But then we have the value of P. P is known to be an integral from 0 to infinity of exponential A transpose of T Q exponential A T dt. Let's call this equation 1. Let's call this equation 2. So substituting equation 2 into equation 1, we are going to have A transpose into integral from 0 to infinity, that is the value of P exponential A transpose of T Q exponential AT dt. Then we're going to have plus A into integral from 0 to infinity of exponential A transpose of T Q exponential AT dt. So this is what we have. So let's solve this further. We can solve this further by saying integral from 0 to infinity, bring this exponential inside. We have A exponential A, this A transpose of T Q exponential AT, and this is plus A, bringing this to the same integral, and exponential A transpose of T Q exponential A of T, right? And this is the T. So remember what we have here is A transpose of P plus PA or AP. Addition is commutative. So this is equal to integral from 0 to infinity of d dt of exponential A transpose of T Q exponential A of T dt. So if you have this, this way, the integral and the differentiation at the same time, integral is the inverse of differentiation and vice versa, which is to say the integral will go with the differentiation, and you will only have to take your limit from 0 to infinity. By that I mean, say you have 2 multiplying 2 raised to the power of 1. This is the same thing as 1 is equal to 1, because 2 inverse is the multiplicative inverse of 2, which means multiplying each other is going to have 1. So if integration is the inverse of differentiation, then it means multiplying the two of them, you are going to have 1. So just take your limit, and this will be A transpose of P plus P of A. So from here, if you take your limit, your upper limit, you are going to have exponential A transpose of infinity Q exponential A infinity minus exponential A transpose of 0 Q exponential A of 0. So of course, this one here is going to go to 0. So, and then exponential 0 is 1 1. So what you are going to have here is minus Q, and this is A transpose P plus PA, and this is your Lyapunov. This is your Lyapunov equation, your Lyapunov function. So they say it has a negative real numbers, which is this negative Q, of which if you bring it to the left hand side, it will become a plus Q. So with this, we are done with the first part of the question, which says it has a negative real part. So we are going to be treating the second part now. For all matrices, there exists a unique solution. So we are going to be showing that there exists a unique solution. Let's come back to our worksheet. So to prove that there exists a unique solution, we are going to let P1 and P2 be any two solutions, where we are going to have two systems of linear equations. We are going to have, that is the second proof now, we are going to have A transpose of P1 plus P2A, and we are going to have, let's bring this side, Q to be equal to 0. Let's call this equation 1. And then we have another P2 plus P2. Okay, sorry, this is P1 plus P2A plus Q equal to 0, and this is equation 2. So let's subtract equation 2 from equation 1. We're going to have A transpose of P1 minus P2 plus A into P1 minus P2, and this minus this will be 0, so this will be equal to 0. And so here let's multiply exponential A transpose of T, right? Let's multiply this on, and then also multiply, okay, let's have this, multiply this P1 minus P2, and also multiply exponential 18 on both sides of the equation. So we are going to have A exponential A transpose of T, and into P1 minus P2 exponential 80 equal to 0. So you can see that this is the same thing as saying you are differentiating ddt of exponential A transpose of T into P1 minus P2 of exponential 80 equal to 0. Is the same thing as saying you are differentiating this way, because if you open this bracket, if you do differentiate this function, you are going to have this. So from this equation here, we are going to have this to become exponential A transpose of T into P1 minus P2 of exponential 80 to be equal to 0. So if you take limit as t tends to infinity, you are going to have P1 minus P2 to be equal to 0, and which indicates that P1 is equal to P2. So we've proven that the matrix, which is from here, we've proven that the matrix of this greater than 0, there exists a unique solution this to the Lyaponuv equation of this. So thank you for watching this video. Please like this video, subscribe to this YouTube channel, and don't forget to hit the notification bell to get notified each time we upload a video. Thank you.